Okay, so I'm going to begin by just saying that there's three types of problems. Oh, do you have a copy of a Moody diagram in front of you?
I have the imperial units one
That's
that's on
fine.
the FE thing.
That's fine. So what you'll notice about it is they're the same, like the imperial ones and the other ones, because if you look at like the axes, like the horizontal axis is Reynolds number, which is unitless, and the vertical axis on the right is the relative roughness, which is unitless, and the friction factor, which is what we're trying to get off of it, is also unitless. The only part of it that is different is if they add the little chart on there with all the what do you call it's on there, the roughness the roughness lengths. So I'm assuming that they call that is it called epsilon on that one?
Yeah, it's epsilon in feet.
Right. So yeah, so if you get a different one, it's just going to have epsilon in units of millimeters usually. A lot of times I'll have it in inches, which is a little bit annoying. I mean, inches is better because usually the roughness elements are smaller, but it's worse because, usually you're trying to non-dimensionalize it by dividing it by the diameter, which is usually not in inches. So anyway, doesn't matter. Okay, so there's three types of problems here that you'll have to deal with. And so there's a type 1, a type 2, and a type 3. And so these are problems that will ultimately mean that these are what we call Moody problems, or the problems where ultimately you're going to need to find this F, this friction factor. And so you have to get that from Moody. And there are three types. Okay, so that's how you know you're dealing with one of these types. And really it's about it's not necessarily what does the problem tell you to solve for. It's about what do you, it's just like what's going to be the big hurdle to getting the final solution. And so really the type 1, usually your big problem is you just need to figure out the head loss. Usually it's the head loss due to friction. So to get the head loss due to friction, it equals FL on D, V squared on 2G. And so maybe that's the whole point of the whole problem. That's certainly a possibility. But more likely to ask for something else. But the final solution, you just need to know this is something that you're going to need to know. So maybe it's like you need to know the head of the pump that's required. Well, to figure out the head of the pump, you need to know how much energy you're going to lose to friction. So you need to know HF. Okay, and so that's the first one. This one is really easy. This is the easiest one. So this is the one that I don't want to say it's really easy, but it's the easiest type. Okay, by far. It's because it's the straightforward one. Then there's a type 2 problem. And in a type 2 problem, let's see, what's the type 2 problem? Okay, the type 2 problem, usually you're looking for V or Q is what you're looking for. Okay, now the problem with that one is this is going to require an iteration. Okay, and then the last one is you're looking for the diameter. And it's usually very clearly the diameter. So this is like the design problem. This is like, okay, you're building, you're building a pipe to pump water from this reservoir to this reservoir. What diameter do you need? So to me, the type 3, that's really the engineering type problem. And you're saying, I guess type 2 maybe could be the engineering type problem. Like they all could be. But, to me, usually as engineers, we're designing a system. And so we're saying to ourselves, okay, well, we're trying to go from reservoir 1 to reservoir 2. We want to have a certain flow rate, or we want to have these, whatever go on. How big does the pipe need to be? Because obviously, if you make the pipe too big, that's fine. It'll work. It'll work even better than the smaller pipe, but it's also going to be more expensive. So we want to just meet the criteria we have so we can save money. So I'm going to walk you through a few of these, and I'm just going to kind of steal some problems off of the internet. If you watch my videos, I've already stolen as many of these problems as I can steal. So it just kind of gets, I'm just going to go easy here on myself by just kind of grabbing these other ones as we go. So I'm going to go ahead and delete this bit, just not all of it, but just that bit. So we'll kind of be able to identify pretty quickly what type we have. So basically these two down here, the bottom two require iteration. So this is an iteration. And if we get an iteration, we're not as happy because that's going to be a lot harder. It's a big jump up from 1 to 2. And then it should jump up from 2 to 3, although it's not really as huge of a jump. Okay, so this one, this is a problem type 2, and it says, okay, it says gasoline. So here's a given gas with kinematic viscosity. So kinematic viscosity is this little symbol, equals 5 times 10 to the minus 7 meters per second, meters squared per second. Flows in a 200, so a diameter, it's got a pipe, 200 millimeter diameter, so 0.200 meters. Smooth pipe, smooth. The friction head loss is 0.43 meters per 100 meters. So let's see, the friction head loss is 0.43 meters per 100 meters. So that per 100 meters is per length. So that's what that is. So I'll read the whole thing to you. It says, when gasoline with a kinematic viscosity of 5 times 10 to the negative 7 meters squared per second flows in a 200 millimeter diameter smooth pipe, the friction head loss is 43 centimeters per meter. I mean, per 100 meters. Find the flow rate. So it says Q equals what? Okay, so if we want to be brainless about this, then I already know what the iteration is going to look like. Now I'm going to propose not being brainless, but so like if you watch my videos for a type 2 problem right here, you can basically start off the problem by saying, okay, I know that what I'm going to be looking for is I'm going to create a chart that looks like this. F assumed velocity from an equation 1, Reynolds number from equation 2, and then an F. And this last F, I didn't leave myself a lot of room, but that's going to come from Moody. Okay, so you could like basically start your problem just by doing this, just because you know that that's what's going to happen. Okay, I don't really like doing things the brainless way. I never like to do things brainless. So, but what we're going to do here is we're going to walk into why this happens. Okay, why do we have to iterate and all that other stuff? So we'll start with, I mean, what's the obvious way to solve this? There isn't really an obvious way to solve this. This is complicated. So somehow we need to get a flow rate, Q, or basically I need to get a V, right? So basically to get that, if I get a V, I know the diameter. So if I get a V, I'm good to go. So I need an equation that's got the V in it and, you know, some other stuff that we know. And so the most obvious thing is to use this tool right here. Okay, so I'm not even using energy equation because I could use energy equation, but the problem is I don't really know a whole lot of information. Like I don't have a 0.1, I don't have a 0.2. I'm assuming there's no pumps and turbines. I'm assuming the velocity is the same at 1 as it is at 2 because it's the same pipe. The pressure between 1 and 2 will drop, but there's a head loss. So, and I don't, you know, so what we're going to do is I'm going to work from here. And basically, I'm going to say, well, HF equals F L on D, excuse me, L on D, V squared on 2G. And that's good because what it does is it's got the thing I'm looking for right here. The problem is it also has this, which I don't know. Okay, so it's got two unknowns, one of which we care about and one which, I mean, I don't really care about F except that it helps me solve the problem. So what we do is, well, I mean, it's a little problematic, but so what I want to do is I don't know HF. I know HF per unit length. So I'm going to take this L and bring it to the other side. So I'm going to get HF on L equals F on D, V squared on 2G. Okay, so a little bit annoying, but I think what we're going to have to do is we're going to have to rearrange this sucker. I'm just going to start plugging in. So this D, I'm going to replace with a 0.200 meters. HF on L, I'm going to replace with 0.43 over 100. Okay, I'm not going to worry about the units there because they cancel. And I'm going to replace 2G with 2 times 9.81 meters per second squared. Come on, you can do it. Come on, there you go. Okay, so then the last thing we need here is we need F, okay? And this is where we're gonna get into why we have a problem here. And so we need F. So I'm gonna go over here and I'm gonna say, okay, we need F. So usually if you need F, right, and let's suppose you didn't have this little guide up here that told us we were gonna have to iterate, we would go to the Moody diagram. Okay, you have the Moody in front of you?
Yeah, I've got it.
Okay, so let's try to use Moody because this will explain why we need to iterate. So we need the x-axis and we need the y-axis. Do you have the x-axis?
No, because we don't know velocity, right?
Right. So it's a Reynolds number, right? And it equals VD on nu, right? So if we knew the velocity, we'd be in good shape. So I'm going to give you as much of this as we can do. So the V, we don't know. The diameter is 0.200 meters. And the nu is 5.5 times 10 to the negative 7 meters squared per second. Okay, so I'll go ahead and rearrange that to make it as easy as possible. So 0.2 divided by 5 to the negative 7. And we get 400,000. And the units on that is going to be seconds per meter. And then we got a V out here. Okay, so we can't do that part. Can we get the vertical axis?
Well, we know that it's smooth and we know the D, so we should be able to get the relative roughness.
Okay, yeah. So what is smooth? What do you think smooth is for the roughness elements?
I don't know, 0? Assume like equivalent to 0?
Yep, perfect. Okay, so that's also one of the reasons why I like this one. Smooth is 0. And whenever I put smooth on a test or something or homework, it always confuses students. And my hope is always like, let's try to nip that in the bud and let's try to have as many smooth problems. If I can make like half the problem smooth, because otherwise, like any other roughness, it doesn't even really matter. Like the problem works the same way, but smooth is just kind of a little tricky. All right, so yeah, so basically we can't get F right here because I don't have Reynolds number, and I don't have Reynolds number because I don't have velocity, right? But that, of course, is what I'm trying to solve for in the first place. So this is our kind of circular logic that creates a problem. So I'm going to go ahead and redraw this. Well, you know what? I'm just going to get rid of these little numbers right here. Okay, because we've now done all the work, Reynolds number, and then F. So what we're going to do is we're going to walk through this chart right here, and we're going to solve these things in order until we get an answer. So the problem here is, so what we're going to do basically is we're going to assume a value for F right here. We'll use that to get a value for V. Use V then to get a Reynolds number right here. And then once we have a Reynolds number, we'll go to Moody and we'll get an F. And what will happen is if we go in this order, it will slowly converge on a solution. Okay, or quickly, it really all depends. The big problem here, the only thing that I want to do is this equation right here is not easy to work with. So because I'm going to use it, I'm going to assume an F, and I'm going to get a V. So what I want to do is I want to solve this in terms of V. So what I'm going to do is I'm going to write it as V equals the square root of, let's see here, 0.43 divided by 100 times 0.2 times 19.62 equals that business divided by F. So it's going to be 0.01687.3. That's 5 sig figs. That's enough. Divided by F. Okay, and wait, where's my meter squared? I should have a Yeah, meters squared per second squared is right here. Okay. So solving it that way just makes it so that this iteration process is simple. So usually on a type 2, what you'll do for your guess is if you look over to the left-hand side, like let's suppose epsilon on D were not 0. Let's suppose it was 0.01. If you look over on the right-hand side, if you can find that line, 0.01, and if you just take that blue line or whatever color it is, maybe it's just a dark black line or whatever, and just follow it all the way till you get to the left-hand side, that would be your best first guess. Because if you look at that solid line and it goes like this and then it slowly curls up, then the most likely answer for you to end up getting off this Moody diagram is for you to slide all the way to the left and to run into, most of it is in that flat section. So that is the most likely answer for you. So that's usually your best guess. The problem is we're at 0. So we don't have such, we're not so lucky, right? Let me bring up a Moody so I can follow along as you do this. Yeah, so what we want to do here, Moody diagram. Let me get one up for me. I always use the same one off the internet. I'm doing that. The one on it's the one on Wiki. I like the blue lines. Okay, so in this case, it's not really clear what to guess because, obviously, if you look at the smooth line for the smooth pipe, it basically your friction factor on the left will range from like, what is that bottom one? Like, I don't know, anyway, basically as low as it can possibly go, all the way up to as high as like 0.05. So what I would recommend in this case is just pick one right in the middle. So you got one you want to pick?
I'm sorry, could you repeat that? I was pulling up the one you had.
Oh, it doesn't matter. It
doesn't. Okay, because it's different, but not like that different.
You should, you'll get the same numbers.
Okay.
So what, do you see just pick a friction factor to guess. Obviously there's no right answer here.
I don't know, 0.02.
0.02, that's what I would have picked as well. You'll note, I've done it, usually when I do this in class, I'll actually show on a spreadsheet. You could pick a number as high as like 100, which is clearly like out of bounds, and it converges really fast. So a lot of people really stress out about the initial guess. Don't stress out about the initial guess. Okay, and in fact, you know what, that's a great one. Let's pick a bad initial guess. 1. Okay, 1's not even on the chart, right? Let's just pick a really bad one. Just to show how quick it'll converge. So then we'll go, okay, 0.016873, square root of that, so the 0.5. Okay, and so we're gonna get a velocity here of 0.12989, 990. This is meters per second. Okay, so basically I get that out of this equation. Then I'm gonna take this velocity right here. I'm gonna put it in here, so I'm gonna multiply that number times 40,000. 1, 2, 3. And I get 40,000. That seems a little small. It's supposed to be 400,000. I think it's supposed to be 400.
Yeah, it's supposed to be 400,000.
Okay, yeah, so let's put another 0 in there. Okay, so 0.12990 times 400, 1, 2, 3, and we end up with 5.2 times 10 to the 4th. I don't recommend worrying too much about significant figures here, because if you look at the chart, we can't really read significant figures that tight. Okay, so go ahead and use your Moody and let's get a friction factor here. Let's see, 5.2 times 10 to the... Should always be careful in this step too, because if you get it wrong, it'll slow down the... 3, 4, 5. Huh.
So So on this point, I go to somewhere where it's flat on there. Is that right?
No. So what you're going to do is, okay, so what you're going to do is, okay, so you need to identify, so you see how I've got all the blue lines, right? So they're flat and then they're curvy, right? And so you need to pick the blue line that works for you. Okay, so in this case, it's the smooth line. So it's the hardest line to work with because it's curvy the whole time, right? So then you need to find on that line the point that has a Reynolds number of 5.2 times 10 to the fourth.
So it's a little bit above 0.02.
Right. That's what you want. Okay, so we'll write 0.02. Okay, now again, like reading this chart is a little bit approximate, so people are going to get different answers. So there's a certain amount of play in these answers, and that I just have to deal with. There are more approximate ways to solve if you use a computer, but on the FE, you're going to have to use this Moody. So on my exam, you have to use the Moody chart.
In that first, so that choice that I like, it seems like it's off a little bit. That doesn't matter because it's just getting me closer, since that was just a random pick, and then we'll go with that one for the next one.
Right, and we're just going to get closer and closer. So basically, until F assumed and F match, you keep doing this. And as you can see, obviously, your first guess would have been a lot better, right? So we'll go ahead and plug that in. 0.016873 divided by 0.02. We're going to raise that to the 0.5. Okay, and we get 0.9185, and basically you just leave that number in your calculator. You know, I mean, you don't even necessarily have to write all this down. You just write this down so that I can grade it. You know, so then you go over to to this equation, and we're just going to multiply that times 400,000. It's not really that time consuming if you set your equations up right. So you go equals, and we get 3.8 times 10 to the fifth. Yeah, so go ahead and let's get another Moody. I'll be doing it as well to make sure that, let's see, 3.8 times 10 to the fifth. Okay, we're 1, 2, 3, almost 4.
So is it about 0.012?
Yeah, or 0.113 is what I got, but I actually prefer to overshoot a little bit because I see the direction it's going in. But if you overshoot, it'll bounce back. So 0.012, and you can see that what's going to happen is each jump is going to get a little bit smaller. Hopefully this is it. Smooth, you can probably tell that, like, if you look at smooth is the worst option that you get. All the other ones have this large flat section. So as long as you're above a certain Reynolds number, you're always going to get the same value. And so those are the ones that you really want to get. Like ideally you have a very rough pipe, because then, above a pretty low Reynolds number, like you don't have to worry about really much of anything. So we'll go, 0.016. I mean, this is good practice, so we'll just kind of keep doing it. Times 0.01, divided by 0.012 equals to the half. And one of the things that to be aware of is if you make an error on your calculator here or reading the Moody, it's just going to slow you down. It'll be a setback, and then it's just going to take more effort. Okay, times 400,000. That's 4.7 times 10 to the fifth. Okay. It looked like you were working ahead of me a little bit. Did you already get the Moody?
No, I got 4.7 also.
Okay, all right, good. 4 points. I mean, it's also nice because you'll get to a point where the Reynolds numbers are so close that you can't even really tell the difference. Let's see, where's my ruler? 4.7, 10 to the 5th, 1, 2, 3.
So would it be like 0.0115? Or I'm not sure.
Yeah, I think that I think you're reading these numbers a little bit different than me. Like I really think it's 0.013. I mean, it is lower than the last one, but I still keep looking at it. I'm like, it's closer to 0.015 than it is to 0.01. Is that not what you're getting?
Yeah, I mean, I'm looking at the one that is in the FE one. Is it's on a different scale.
Sure.
Right.
Sure.
So it's like there's more like minor axes between 0.01 and 0.02.
Oh, I see. Okay.
So I don't know if that's leading.
Oh, so are you using the FE one?
Yeah, I'm looking at the FE one. I have the Wikipedia one pulled up on my other screen, but
okay, then we can use that. No, I think really you should just go to 2 significant digits and not, so if you see 0.012 again, that's fine. I don't think there's a lot of value to trying to parse 0.0115. I mean, you could do that if you wanted to, but 2 significant figures is fine. Okay, so we'll go ahead and call this. Let me go ahead and see what the, did I lose the problem? Oh yeah, so the problem, I found this problem on the internet, and they ended up with a number of 0.0134. Okay, so, whatever, but they were probably using a different Moody or whatever. I mean, to get to 0.0134, I mean, there's just no way to look at the chart and really get that much precision. So yeah, so then what do we got to do to solve the final problem?
So we just plug that back into our V equals square root.
So we take this, no. So basically, once this matches this, we're done iterating. So now we're done. So this number right here, this velocity, that's the velocity in the pipe.
So we just multiply that by pi d squared over 4.
Yep. Yeah. So we would just say, and I mean, to me, that's kind of trivial at this point in the course, like, but we'll go ahead and do it just because. So we'll say Q equals 1.1858 meters per second times pi over 4 times the diameter 0.2. Come on. Squared, meters squared. Okay, so Q equals whatever that is. 1.1858 times pi divided, hit clear. Times pi divided by 4 equals times 0.2 squared. Okay, so it's a pretty small number, 0.037. I'm just going to give you 3 sig figs, 3 cubic meters per second. Okay, and that would be the final solution to this problem. Okay. The only thing to be aware of here, just because I think that, a lot of people want kind of like I don't know what the word is, like a cut, like a copy and paste solution, is that this, so with these types of problems, the equation to get the Reynolds number is almost always just, this straightforward. The equation to get V can be, and often is, a full energy equation that just kind of reduces to something like this. Okay, it usually has a form like that, but whatever it is, it's basically we're looking for an equation that has V in it and has F in it. And a lot of times it can be a lot uglier than this.
And so it's just, since this one we were given head loss.
Yeah.
Otherwise we'd have to calculate head loss and then plug that in, right?
Yeah. So like a more common thing, let me erase. A more common way that this looks is like, okay, and we haven't gotten to the minor losses, but I'll kind of just explain that to you real quick, but it's much more common to actually do an energy equation. So you'll, like, let's suppose we've got a system and we've got a tank over here, and then you've got some bends, and then you've got like a valve right here. You could even have a, you know, a pump or something right here. And then, I don't know, and then the water exits into another reservoir or something. Let's just imagine. Okay, so you've got something like this. And so we're going to do an energy equation from 1 to 2. Okay. And so this is what that energy equation is going to look like. You know, so we're going to have this, some sort of datum. So we're going to have, on the left-hand side, there's no pressure, there's no velocity, there's only elevation, Z1. Okay, there's a pump between 1 and 2, plus the pump. Okay, on the right-hand side, there's no pressure, there's no velocity, C2. Okay, so maybe we just call the elevation difference between these two H. So I don't have to deal with both of them. So we've got H plus H of the pump. And on the right-hand side, okay, equals, okay, so now I've got no elevation because I've already accounted for that. I've got no pressure and I've got no velocity. So the only thing I've got left is the turbine, which doesn't exist, and the head loss. And so we've got two forms of head loss here. And one of them would be F L on D, V squared on 2G for all of these pipes. And the other one would be a head loss due to all of these fittings, due to the, you know, this entrance, that bend, this valve, and this exit. And so those are the minor losses. And we haven't talked about those minor losses, but basically what's going to happen for each of these is this has a K for the entrance times V squared on 2G. That's the head loss. This has a K for a bend, V squared on 2G. This, the head loss, is K for a bend. So it's the same as this one, if it's the same bend. This has a K for a valve, V squared on 2G. This one has a K for an exit, times V squared on 2G. And all of these Ks you just look up on a chart. Okay, and so the net effect of all of them is the sum of all the Ks times V squared on 2G. Okay, and these vary. You know, for the valves, they can be as high as like 10, the K. I'm sure they probably have valves that are even higher than that. And that really kind of stinks when you're losing 10 times your velocity head to one valve. And for the bends, they'll vary. And for the entrances, they might be 0.5. For the exit, it's for a big exit like this, it's usually 1.0. In fact, that makes sense because if you think about our HDL and EGL, the amount of energy lost there is always V squared on 2G. And that's really because the other way to think about it is that the K value is 1. Anyway, so you would take this equation right here and you would pull out V as a function of F. So you basically get it, like if this were your problem, you'd be looking for this equation right here. And so what you would do is you'd take these two V squareds and 2G, you kind of pull them out. And so you'd end up with your right-hand side, or it would be, let's see if we can go right here, H plus HP divided by FL on D plus the sum of the Ks equals V squared on 2G. And then you would solve that for V as a function of F, because you would know all the rest of this. I mean, if you didn't know all the rest of it, then you'd be like, well, I just can't solve this. You know, so that's the idea. Okay, does that make sense? Kind of like how it would be a little bit, it's just more involved. It's not.
Yeah, I got you.
Okay. Yeah. So, I mean, what happens a lot of times is people try to memorize that this is the answer. And it's like, no, it's something coming from energy equation. You know, just whatever you can do to get V as a function of F. All right, so let's see if we can find, now if you get a type 1 problem, basically you just read the Moody diagram. You're able to solve for the Reynolds number and the relative roughness right off the bat. So you just read a number off of the Moody diagram and then you just solve. So the type 1s to me, I don't want to say they're trivial, but by comparison, they're trivial. Let's see if I can't find a nice type 3. I'm going to clear all that. Let's see if I can find a nice type 3. I may have to go to, you know, there's not really a lot of type 3 problems out there. Let me go to, I'm going to go to my old homework. So I'm going to go to Moodle, because I know I have assigned some type 3s in the past. And I think when you're in hydraulics, you can do a lot more with that type 3 stuff. Let's see here. Let's go down to old homework. Let's see. Energy with minor losses. Nope. That stinks. Let's try energy with friction losses. Oh, here we go. Okay. All right. So this one doesn't have a lot of words in it, but it says water is to flow at a rate of 1 cubic meter per second. I hate 1, so let's make it 2. Because if I use 1, then you can't necessarily tell where I put it. Through a rough concrete pipe. Okay, so concrete. Now, what's annoying about concrete is, in this case, the roughness. Like if you look at your Moody diagram, whichever one you have, usually, like, does it have a roughness for concrete?
Well, it has 2, right?
Right.
One that's like concrete lined, right? And then one that's just concrete. I don't know.
Okay, right. And so if it doesn't, so that can be the annoying thing, right? Is you have to make a decision. In this case, I would tell you to choose the one that just says concrete. What does it say for the roughness?
0.001 to 0.01 in feet.
0.001 to 0.01 in feet?
Yeah.
So obviously this is a problem for us because, you know, well, so there's 2 things. First of all, it's a problem because clearly you can't use feet when I already gave you Q in cubic meters per second. The other problem is it's got this range. So if I don't give you, a value for a roughness and it's got a range, choose a number that makes your life easy. You know, so, I mean, in this case, obviously you can't use that Moody diagram at all because it's got the wrong roughnesses on it. But if this were in the imperial or the British units, I'd be like, well, I like 0.01. So just write down epsilon equals 0.01 and I'll have to deal with that, right? That's my fault for not giving it to you. Okay. So usually what I will do is I won't actually make you use that. I'll override that, whatever the chart says. So I'm just going to say a concrete pipe with a roughness of 0. Let's see. It just says 3 millimeters. Okay. The other thing that I'll notice, if you go back to my old homework, a lot of times instead of this, you'll see in my old stuff, I do KS equals 3 millimeters. This is from the old textbook. Okay. So if you see that KS in some of my old problems, it's just something I need to go through and spend an afternoon like searching all my documents for KS and replacing with an epsilon. It's just like such a small, simple project that'll take me, 30 minutes and I just haven't gotten around to doing it.
So that number seems really high though, is it not? Like that 3 millimeters? Because when I'm looking at the one on Wikipedia, it says the concrete is 0.25. So that's like that's a whole order of magnitude higher, right?
But it says 0.25 millimeters
for concrete. Yeah, that 3 is for, it says for old sewers.
Huh. Well, yeah. So definitely sounds high then. I mean, even imagining concrete, it's hard to imagine it having 3 millimeters. I mean, 3 millimeters is, it does seem very high. I guess, let's go ahead and work this problem with a more realistic number. I think, in this case, I copied the problem from somewhere. I don't make up too many of my own problems because when I do, there's usually errors, except for the twisty straw one. 0.25 millimeters is what you had?
Yeah, that's what for a coarse concrete.
Okay, then we'll take that. Okay, water is to flow at this rate, connecting two lakes. Determine the diameter of the pipe needed if the elevation difference between the lake water surfaces is 10 meters. So Z2 minus Z1 equals 10 meters. I guess Z1 minus Z2 because it's going to go from 1 to 2. All right, so Z1 minus Z2 equals 10 meters. And the pipe length is 1,000 meters. Okay, and then it says neglect minor losses. Okay, so, and then K equals 0 for all everything. Okay, so I'll read it again just so it all makes sense. Okay, water is to flow at a rate of 2 cms through a rough concrete pipe that connects two lakes. Determine the diameter of pipe needed if the elevation difference between the water surfaces is 10 meters and the pipe length is 1,000 meters. Okay, so I'll draw a quick picture of that. So we've got a lake here, and then we've got a pipe, and then we've got a lake here. Okay, so for whatever reason, you know, they want to control, they want the water to flow from one to another, and they want to be able to control the rate at which it flows, or they want to have at least X number of, you know, cubic meters per second. Okay, and so this thing is 1,000 meters, 1,000 meters long, a kilometer, and the elevation difference between these two is 10 meters. Okay, and I think that's pretty much everything we can draw on there. I mean, obviously you could draw that it's concrete if you wanted to, but whatever. All right, so right now, like if you looked at what I did earlier, you could identify right off the bat that this is a type 3 problem by the fact that the diameter is unknown. But what we're gonna do is, I'm gonna pretend we don't know that, and I'm just gonna try to solve it. Now we're gonna run into a case where we have to iterate, but I'm gonna delete that. I'm just gonna have to remember that because space is gonna be a premium here. So I'm gonna delete the things we've already drawn on there. We've already drew that on there. Okay, so here we go. Okay, so can I get a draw? Okay, so we're gonna. Okay, so what we're gonna do is we're just basically gonna straight up try to solve it. I'm gonna start here. I'm gonna go to here. Okay, 1 to 2. Okay, you should almost be getting bored of the 1s and the 2s and eliminating terms, but P1 on gamma plus Z1 plus B1 squared on 2G, this is an alpha, plus HP equals P2 on gamma plus Z2 plus alpha V2 squared on 2G plus HT plus, I'm gonna go ahead and split out the head loss, HF plus HL. I'm gonna quickly kind of get rid of everything. I think you, at this point, know what we can get rid of. We can get rid of these pressure terms because it's atmospheric. We can get rid of the velocities because it's on the surface. We can get rid of this HP because there's no pump. We get a HT because there's no turbine. And we can get rid of these minor losses because it told us to ignore all minor losses. Okay, so we're left with C1 minus Z2. I'll have that over on the left-hand side. So that's gonna be 10 meters. Let me do this in black. So 10 meters equals HF. F, okay, and that's where we know we're doing Moody problems because we have that F. L on D, so L is 1,000. I guess I'm going straight into plugging in. I didn't mean to. Over D, and then V squared on 2G. So that's going to be 2 times 9.81 meters per second squared. Okay, hopefully you can see what a mess this is. We have 3 unknowns now. And of course, the biggie really here is F. Can we shrink this from 3 to 2 unknowns? Or better yet, do you know how we can shrink this from 3 to 2 unknowns?
Well, we know that F isn't F. Oh wait, no, never mind. I was thinking of relative roughness. That's not
Right.
Same as the friction factor.
Right.
No, I'm not sure.
How do we normally deal with when we've got a V and we've got a D?
Well, that's how we get the Reynolds number, right?
Right.
Which is V, that'd be V times D, but this is V over D. Oh, we have Q, which is...
We have Q.
So then that's V times A, right? Which is V in terms of V and D.
Yeah, so basically we can say Q equals VA. Q equals V times pi over 4 times D squared, right? So we can get a relationship between the two if we wanted, okay? And that would actually be very much to our benefit. So let me see, hold on one second. I'm actually suddenly brain farting as to what the order is that we want to do this. Give me one second. Okay, yeah, so so what we're going to want to do, let's see here. Okay, so okay, I'm trying to think better how to explain this. Okay, let's go look at Moody real quick. Okay, so you'll see why this is the most complicated right here when you look at Moody, because you know at some point in time we're going to need F, right? Can we get the relative roughness?
Not directly.
No. Not directly, right? What about the Reynolds number?
Oh, that's the same problem.
Right.
We don't know D.
It's actually even worse because we don't know V and we don't know D. Okay. So we kind of have problems all over the place, right? So then we've got this other, so we need to figure out Reynolds number, and we need to figure out the relative roughness, epsilon over D. Now, epsilon over D roughly is like kind of trivial, right? We know the epsilon is so 0.00025 meters over D. Okay, so that's an equation. Okay, the Reynolds number is VD on nu. I'm gonna erase this because we're gonna come back to that in a second, but we are gonna use that. But okay, so Reynolds number, oh, come on. Reynolds number equals VD on nu, but I don't want to deal with both V and D. So ultimately, I think because we're trying to get everything, we're trying to solve for D. So I don't really want to worry about V, right? So what I want to do is I want to solve everything in terms of D. So we're going to take this Reynolds number, and in place of V, I'm going to put Q over A, like that. And then in place of the area, I'm going to put pi over 4 times D squared times D over nu. Are you following what I'm doing here?
Yep, I got you.
Okay. All right, so then Reynolds number becomes, let's see here, there's going to be a 4 on top, a Q on top. Looks like there's going to be a nu and a D on the bottom, and a pi on the bottom. So pi nu D and 4Q. I think that's everything, right? Yeah. So let's go ahead and make this equation easy to solve by doing 4 times what's Q in this case, 2.0 cubic meters per second divided by pi. Nu is this water? Yeah, this is water. So it's I think it's 10 to the minus 5 meters squared per second. Should probably look that up real quick. By the way, if you don't have a good place to look up the viscosity of water, I recommend the engineering toolbox. Just because it'll, like, if you type in engineering toolbox and just bookmark it or whatever, and you go down there they'll have a chart for the viscosity of water. And if you go down, and if it doesn't have a temperature, then I recommend for English units, use 50F, and for what do you call it units? For SI units, use 20F. I mean, excuse me, 20C. And so at 20C, if we scroll over, we're going to see basically it's 1 times 10 to the negative 6. So this is going to be 10 to the negative 6 meters squared per second. And I really don't even recommend worrying about the 1, because if you go to the if at 50F, you'll see it's 1.4. It's 1.4 times 10 to the negative 5th feet squared per second. That 1.4 doesn't really matter because we're just trying to get an order of magnitude. So I wouldn't worry about that too much. So the Reynolds number, if we make this an easy equation, is going to be.
That should be a D on that last one.
Oh,
you wrote an extra new.
Yeah, D, thank you. Okay, so let's see here. We're going to get 8 divided by pi. It's not going to like, oh, it did like that. Okay. Divided by negative 6. All right, so it's a really big number. 2.5455 times 10 to the, let's see, 1, 2, 3, 4, 5, 6. I really need to learn where the scientific notation button is on my calculator. And it looks like that. Okay, it looks like it has some meters up here. Okay, so that's the Reynolds number. Okay, now we want to take this equation that we have right here, and we want to, so this equation is easy. And now we need to do the same thing with this equation right here. I need to get rid of some unknowns here. And so we're going to do the same thing. We're going to get rid of, and you know what, I'm going to go back to symbols because this is going to be way easier to solve in symbols. So we'll call this H. That's the difference between Z1 and Z2. Call this 1000. I'm going to just call that L. Okay, and this will be 2G. Okay, and then, so let's see. So instead of V squared, I want everything in terms of D. So I'm going to get rid of that V squared. I'm going to do Q over A squared. Q over A squared. I really hate doing it this because the algebraic error possibilities here are endless, at least for me. L on D. So now we've got Q squared on A squared, which is pi over 4 times D squared squared all over 2G. Okay, so H equals, okay, let's see. 4 on pi, F, L on D to the 5th. So we've got a 2G on the bottom, got a Q squared on the top. Sorry, they should never let me solve these kinds of problems, especially not in public. Is that what you're getting? Did I make an error in there?
So I got FL, I got 16Q squared.
I forgot to square the 4. Right, okay, go ahead.
16Q squared over 2 pi squared D to the 5th G. And then that's times FL.
Yeah, okay. So that's the same as what I got. It's just mine's uglier.
But and also you didn't square the pi.
Oh, you're right. I forgot. Yeah, you know. Yeah, thank you. Exactly. Okay. So yeah, so I get. Yeah. I mean, I hate this problem only because of the algebra.
Yeah, I solved. What made it easier was I went ahead and solved for V as 4Q over pi D squared.
Ah, okay.
And then that was a little bit easier to square than.
Okay. Fair enough.
That other.
Okay, so then what we're going to do is we're going to rearrange this in a way that it's going to work for us. And so one of the things that helps here is to know what are we going to be assuming. Because so basically what we're going to do is it does help to know what we're going to assume. And here's the thing. When I took this course in 1990, whatever year that was, 1998 or whatever year it was, they didn't tell us what to assume and they didn't tell us what to put in next. So you can assume whatever you want. You can assume a Reynolds number and from there you could work the problem. Actually, that wouldn't really help you very much. But you could assume a velocity, a diameter, a friction factor, whatever it is you wanted to do. but there is a thing to assume that will make it like work out the easiest, okay? And so in this case, we're gonna assume a diameter. Okay, so this is gonna be the diameter is gonna get assumed. Okay, and the reason we wanna do the diameter is because once we do the diameter, I can solve for this and I can solve this one. Okay, so from there I can get the relative roughness and I can get the Reynolds number. Okay, once I know those two things, then I can do my Moody diagram and get F. Okay, I'm gonna get that from Moody. Okay, once I've done that, then I have everything to solve this equation for D. And there are other ways that you can do this. It's just that what they didn't teach us was what order and what direction to go in, because you could do this backwards. And like I used to do it where instead of converging, my answers were diverging. And it's because I was doing it in the wrong order. And all I really needed to do was stop and start solving the problems backwards instead of forwards. You know, like I was going like this and it was diverging. And instead I needed to realize I needed to go this way. Like I had written my thing in the exact wrong order. So I would just recommend, don't do like I did. So this thing then needs to be solved for this equation here needs to be solved for D, because by the time we get to this equation right here, we're going to have everything else. So, so if we rearrange this, it's going to look like this. Let's see. Oh yeah, so it's going to be D equals the fifth root. We love fifth roots of 8, because that 16 and that 2 are going to combine. FL Q squared over 2G.
Just over G, not 2G.
Oh, right. Thank you. G pi squared and H, I think.
That's what I got.
Okay, cool. All right, so then again, it's nice if we make that like easier on ourselves. So let's go ahead and plug in some numbers. Come on. Thank you. Okay, so we're gonna do the fifth root of 8. The length is 1,000. Q squared is 2.0 CMS squared. And put the F out front. Divided by 9.81 meters per second squared, pi squared, and then the H was 10 meters. Okay, so that's going to be the fifth root of, I guess that's what the calculator's for, isn't it? Okay, now we should expect a pretty big number under here. I guess, maybe, I don't know. I guess it wouldn't be the end of the world if it was a huge number. All right, so 8, 1, 2, 3 times 4 divided by 9.81 divided by pi squared divided by 10. So 33,051,051, and the units there are, I wrote feet, sorry, this is meters. Let's see, we got meters to the 6th over second squared times meters over meters to the 2nd squared times meters. So we get meters to the 5th, which is exactly what we want, right? Is that a 1? That's a 1. Meters to the 5th times F. Okay, so good. When the units work out, you have to feel pretty good about yourself. All right, so then we're just going to iterate. Now, we're not going to have time for another problem after this. Now, the last question here, because this isn't so obvious, what do you want to guess for your assumed diameter? Any idea how you'd get at a good guess?
Well, since it's iterative, can't we just guess anything?
Yes, yes. So what's a,
I don't know, 1 meter?
that's what I recommend. I always recommend either 1 meter or 1 foot. Or if you prefer, if you had some kind of intuition and you're like, it's going to be a big pipe, go with 100 meters or 10 meters, but pick something easy. There's no reason to pick a hard number. So we'll go 1. I'm going to go ahead and I'm going to put the units above it. Meters, unitless, 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 meters. Okay, so then we just do 1. And then the, so we solve this equation right here. We get 0.00025. We do our Reynolds number. We get 2.6 times 10 to the 6th. Okay, go ahead and do the Moody. Which Moody are you using? I'll use the same one.
Well, I'll use the one on Wikipedia since that's the SI one.
Okay.
That way we got the number.
Okay, so let's see here, 2.6. So if you have one to write on, what can actually help, like on an exam or something, especially if you just printed one out, you can just take a highlighter and highlight the relative roughness that you're on. And that makes it a lot easier. Let's see. F Moody, 2.6 times 10 to the 6th. And 0.000. Oh yeah. 0.0002. So that's 2.5 times 10 to the negative 4.
Is it like 0.012? That
I'm getting 0.15. Let's see if we can't figure this out. So let's see. So you're at are you at like, okay, so are you at just a little bit above the 2 times 10 to the negative 4 line for the relative roughness?
Yeah. Oh, I was right below it, I guess.
Okay. Yeah. So you want to be a little bit above it.
So, I mean, it does it have to be on one of the lines or it doesn't have to be on one of the lines?
No. So basically you're going to imagine a little line following, like roughly following that 2 times 10 to the negative 4, but just a little bit above it. And so it's going to start to kind of curl up a little bit. So maybe, your little imaginary line should start to curl. Because by the time you get to what, 2.6 times 10 to the negative, times 10 to the 6th, maybe it started to curl, maybe it hasn't. But that point should be just a little bit below the dotted line that goes all the way to 0.015.
I gotcha. I see that now.
Okay, you see that now? Okay. Okay, so then we'll erase that. So yeah, reading Moody diagram is, especially if you're not directly on one of the lines, it's frustrating. Okay, so then we just need to get the diameter from there. So let's see here. 0.015 times 33.051, probably excess sig figs there. So 0.495 to the 0.2 power equals 0.869. Very nice. 0.86907, whatever. Okay. So then we'll do it again. 0.86907. And then we're just going to kind of do the same procedure. So we'll raise that to the -1 power, multiply times 0.0005. 0 to 5, and we get 0.00029. Okay, so just a midge smaller, a midge bigger. The Reynolds number is, let's go find that thing. Okay, we're going to multiply that times 2.55 exponent 6 equals, no. 2.9 times 10 to the 6th. So you can see, like, as far as the space on the Moody diagram, which is determined by these numbers, we haven't really moved all that much, but that doesn't mean it won't be annoying. 2.9 times 10 to the 6th. That's a little bit easier because we're pretty close to 3 times 10 to the 6th.
So is it going to be 0.015 again?
Yeah, I'm not getting really any difference. So as soon as you see something like that, you're like, oh, sweet, because then you don't even have to do this calculation again, right? So you're like, all right, cool. We check out, we're good. This is the diameter. So you say D equals, 0.869 meters. And really you might say to yourself, you know what, I bet they don't sell that, So on problems like this, you might go, okay, we're going to want the smallest pipe that's going to work. So in this case, it might be a 90 centimeter pipe if they sell that, if they don't, or maybe a 1 meter pipe, I don't know. That's the most likely. But for this class, just give me give me 3 sig figs, And this is, of course, also another clear example of, I had a student, when I told him I only wanted 3 sig figs, one of the students said, I don't really feel comfortable doing that. Like, it just seems weird. And I'm like, yeah, it does. But I mean, when you think about what it is that you're trying to do, they don't commercially make 86.9 centimeter pipe. It's just, and you're not going to special order for something that's going to go a kilometer. You're just going to go a little bit big, so whatever that might be. So yeah, so I kind of like this problem because I like the idea of doing a design problem. It appeals to me. So
one of these going to be on the test is what you're saying, but the fact you like it so much.
Maybe. I mean, I guarantee you will have a type 2 or a type 3. The type 3 is a little bit more involved. It's really not a ton more involved. There's a lot more algebra involved. A type 3 has not shown up on my final yet. But it's like, I just roll a dice, and it's like, there's a 1 in 6 chance I'll give you a type 3. If I give you a type 3, so then there's a 5 in 6 chance I'm going to give you a type 2. But if I give you a type 3, then basically some of the other problems on the test will be shorter to accommodate, so you'll have more time. So actually, for some people, that might work out really well, because they might go, I don't know how to do a type 2 or a type 3. So please, let's get a type 3. I'll lose my points there, but it'll make everything else a little quicker, So I don't know. It's all, you want every question. All I really want from the test is to make sure you guys study everything. And then hopefully you do well. That's the hope.
I mean, I appreciate the way that you do these tests. You seem to put a lot of work into these tests.
It stresses me out. So it's like it keeps me awake at night that there's going to be some massive problem, and I'm going to have to fix it, and people are going to feel cheated, and that's obviously not the goal. So, or maybe they actually will be cheated, and that would be even worse than them feeling cheated. So anyway, so that's all we got time for. Any questions?
No, I don't think so. I'll just have to find, it's like you said, it's hard for me to find problems like this to practice, right?
Yeah. If you watch my videos, I've because people really have problems finding type 3 problems, I had to have to scour the internet for them. But I mean, they basically usually just boil down to, we have some situation, and it's like, there's almost no words to it. It's like, we've got a pipe, it's connecting these 2 lakes. I mean, that's about all you can put the minor losses in there, but they usually don't. And the reason for it is because they usually teach minor losses after they teach this. So I always put my minor losses in my type 2 problems. In these, I think it would make the algebra very unpleasant.
But it seems like this is the kind of problem that would be like, you could just give us this problem and it would show that we've learned everything. Right?
Yeah, I mean, it's got continuity in there. It's got energy. The only thing it doesn't have is momentum, you know, and momentum will show up a fair bit in, not a ton, but it will show up in hydraulics. Some of these other things, like I don't think you're gonna have manometers in hydraulics, but you will need to know hydrostatics. So anyway, that's all I got. I hope you're enjoying your one-on-one. You know, you get.
Yeah, I appreciate it. I like it.
Yeah, you're getting.
No one else wants to come. That's fine with me. I like it.
Yeah, you're getting your tuition worth. So
absolutely,
yeah.
You're just going to be sitting here doing it anyway. I might as well jump in.
Well, if no one jumps in, I wasn't going to do it. I was like,
okay.
I mean, I guess I don't know. It's like, well, how is that different than my lecture? You know, like why don't I just say, watch my lecture? You know, so yeah. Anyway, all right, Paul. Have a good chat.
All right, you too.
Are you from Pittsburgh or something? You just like the Pirates?
No, my dad is. I just like he raised me a Pirates fan. If New Orleans had a baseball team, I'd be a fan of them. But
well, the one nice thing about Pittsburgh is that all their teams have the same colors. So
yeah, absolutely.
And they kind of match Saints colors, so you could wear that to a Saints game if you want.
Well, it's not quite the same as Saints colors.
Well, of course,
right? Saints are gold, and this is yellow.
Right.
So it's a little clashing. You know, whenever the Saints and the Steelers play, it's like clashing.
Okay. Well, I always just felt like if I lived in Pittsburgh, I would just buy a black and yellow shirt, like probably just even like a polo shirt, and I'd be like, I'm done.
Yeah, absolutely. One size fits all. Right?
Yeah, they really messed up actually, because like living here, every now and then the Pelicans come out with a new jersey or something, and I'm like, oh, I like that. Like I might want to buy that, but you know,
I'd love a black and gold Pelicans jersey.
That'd be cool. They should do a one-off, because you know with the NBA they're like, we have 8 different team colors, and you know we wear them on different nights, and you're like, I don't even know what your uniforms are. So
yeah, I got you.
Yeah. All right, man. Well, yeah, have a good day.
All right, you too.
Technically. So yeah, have a good weekend.
All right, I'll see you on Tuesday.
Sounds good. All right, man. Bye.
All right, bye-bye.
Let's see. Stop recording.